Hey there, chemistry students. In our last lesson, we talked about some of the general layout of the periodic table. And today what we're going to do is we're going to talk a little bit more about the layout of the periodic table, but we're going to focus less on individual elements and more on groups of them, right? On the periodic table, the elements that fall into the vertical columns together, we tend to call them families of elements. And today we're going to talk about some of the different families of elements. You know that their electron configurations should be similar because they fall into a vertical column together. And because their electron configuration is similar, they're going to have similar properties. So these families of elements are elements that have similar properties. We're going to talk about some of them, some of the different families of elements, and we're still working on the target of being able to describe the organization of the periodic table. So let's go ahead and let's talk about some of those families. Okay, the first family to talk about here is a family of just one element. Hydrogen is often considered to be a family just by itself, right? So the hydrogen family consists of hydrogen. Some interesting things about hydrogen. Hydrogen is an invisible gas. You can't see it. It's invisible. It's also explosive, right? It will explode if you set fire to it. Hydrogen is a nonmetal, which is, hydrogen is placed on the left side of the periodic table where all of the metals are. Hydrogen is the only non-metal that's on that side of the table. It's kind of interesting that if scientists believe that if you put hydrogen under, high amounts of pressure and temperature, it might turn from a non-metal into a metal. In fact, that might be what gives some of the gas giant planets some of their magnetic fields. Let's see, hydrogen, really interesting thing, is the most abundant element in the universe. More than 90% of all of the atoms in the entire universe are hydrogen atoms. Hydrogen is probably the most important element for astronomers to understand because things like stars and gas giant planets and most of the nebulas are out there. In fact, most of everything is made out of hydrogen because hydrogen, 90% of all the atoms in the universe are hydrogen atoms. So it's a very important element for astronomers to understand. In fact, astronomy is kind of where the other elements come from. Inside the cores of stars, a process called nuclear fusion takes place, where atoms of hydrogen get squished together to make atoms of helium. And then atoms of helium get squished together to make atoms of larger elements. So most of the elements on our periodic table began as hydrogen atoms in the cores of stars. So hydrogen is the smallest element. It is sort of unique. It is the origin of most of the other elements. Hydrogen is a really interesting element. Okay, the next family to talk about here is the alkali metals. The alkali metals will react with water to form a solution that is alkaline, which is why they're called alkali metals. They'll react with water and they'll form an alkaline solution. Alkaline means that it's, kind of like the opposite of an acid, right? So if you put an alkali metal in water, you'll get something that's a base, alkaline. Right. On the periodic table, the alkali metals are in column 1. All of the elements in column 1 except for hydrogen are alkali metals. That includes lithium, sodium, potassium, rubidium, cesium, and francium. All of the alkali metals have some similar properties. They're all soft, shiny metals. When we say they're soft, what that means is you can cut them very easy. These are metals, and you can easily cut them with, say, a butter knife, right? I mean, they're very soft metals. The alkali metals are all very reactive. They will react with other elements very vigorously. They will react with water. I have some sodium. I'm going to put it in, I have a video where I put it in some water and you can see it react. And I'll cut that into this video. As you go down the periodic table, as you go down that column, they become more and more reactive. So if you put some lithium in some water, lithium will react with water, but it'll kind of fizz a little bit, right? If you put sodium in the water, it'll fizz and then it'll kind of burn a little bit. If you put some potassium in the water, you're going to get, more burning. Each one, as you go down the column, reacts more and more vigorously, right? By the time you get to, say, rubidium, you drop it in some water, it pretty much explode, right? Let's see, all of the electron configurations of the alkali metals are similar. They all end with an S1. So lithium is 2S1, sodium is 3S1, potassium is 4S1. So they all end with a S1. And this means when they form ions, ion is an atom that has the wrong number of electrons. And the alkali metals will all tend to lose one electron. So they end up as ions that have a positive charge, a positive 1 charge. Alright, so here in this container here, I've got some sodium. And sodium is an alkali metal, and an alkali metal will react vigorously with water. And so what I'm going to do is I'm going to take a piece of sodium, and I'm going to show you how it reacts with water. I would do this with all of the alkali metals, but sodium's the only one I have. Now, sodium and alkali metals in general are so reactive that they will react with not just water, but with moisture in the air. And so you have to keep them stored underneath oil. So when I open up this container of sodium, there's some oil in there, and the pieces of sodium are in that oil. Let's see if I can't snag one out here. And even being stored under that oil, they still get this kind of coating on them from reacting with water. So it kind of looks like sort of a nasty tooth, but if I cut into it, which isn't all that difficult to do, then I might find some actual metal in there, some sodium metal left over. I'm not sure this one has any left. Let's see what happens. See what reacts with the water. Bubbles and fumes and whatnot. See most of the white coating, I don't know if you can see, but most of the white coating that was on it is sunk to the bottom. There's just 2 tiny little pieces of sodium fizzing around on the top there. Fizzing around, and it's smoking. Pretty neat stuff. Next family to talk about here is what are called the alkaline earth metals. And a lot of the alkaline earth metals sounds very similar to the alkali metals. They're called alkaline earth metals. Alkaline comes from the fact that they will also react with water to form alkaline solutions. But the earth part, these elements will react with oxygen in a 1-to-1 ratio. And these compounds of these elements and oxygen once upon a time were called earths. So you might have had like magnesium earth, which today we would call magnesium oxide, right? All of these form those kinds of compounds. And so the family is called the alkaline earth metals. These ones are in column 2 on the periodic table. They include beryllium, magnesium, calcium, strontium, barium, and radium. Let's see, they're all shiny metals. They're silvery white in color. They're also fairly soft, but they're not as soft as the alkali metals. They are very reactive, but they're not as reactive as the alkali metals. They will still react with water. If you put them in water, they will react. Some of them sort of vigorously. They all have similar electron configurations. They all end with an S2. So beryllium is 2S2, magnesium is 3S2, calcium is 4S2, and so forth, right? And because they all have those similar electron configurations, they'll form ions in similar ways. All of these will tend to lose 2 electrons when they form an ion. and so they will end up being ions with a positive 2 charge. So the alkaline metals and the alkaline earth metals are over on the left side of the periodic table. Now let's jump all the way to the right side of the periodic table. In column 18, you find the noble gases. The noble gases are helium, neon, argon, krypton, xenon, and radon. All those ones in column 18. There's actually a brand new one at the bottom of that column called oganesson, and as far as I know, scientists aren't sure yet if it shares the same properties with the other ones, so it's not officially a noble gas at this point, as far as I know. But all the other ones in that column are noble gases. The noble gases are all invisible gases, you can't see them, and they are extremely unreactive. Okay? The noble gases do not want to form any kind of compounds. They don't want to react with anything. They all have electron configurations that end with a p6, except for helium, which is only a 1s2. So either way, they have a valence electron level. Their last orbital is completely full, which is why they don't like to react. And as far as forming ions, the noble gases don't form any ions because they have that last outer orbital is full. And they're happy, and they don't want to do anything. Next to those noble gases, in column 17, you find the halogens. These include fluorine, chlorine, bromine, iodine, astatine. And at the bottom of that column, there's a brand new one, tennessine, which, just like the other one, is brand new, and as far as I know, scientists don't know yet if it shares properties with the other halogens. So the halogens, fluorine, chlorine, bromine, iodine, astatine. Some things about them. They are very reactive nonmetals. The halogens will react extremely vigorously, extremely strongly with alkali metals in a 1-to-1 ratio. The halogens will form strong acids with hydrogen. If they react with hydrogen, it forms a strong acid. So hydrogen and fluorine forms hydrofluoric acid, hydrogen and chlorine forms hydrochloric acid, and so forth, right? And they're strong acids. All of the halogens have electron configurations that end with a p5, right? And so that causes them to form ions. They will tend to gain an extra electron, whereas the ones on the other side of the table lost electrons. The ones on this side of the table will tend to gain extra electrons. And the halogens will tend to gain 1 extra electron, which will give them a -1 charge. Alright, to the left of your halogens, you find the chalcogens. Okay, the chalcogens are also often called the oxygen group because nobody remembers the word chalcogen and oxygen is at the top of the group. So it's often called the oxygen group. These include oxygen, sulfur, selenium, tellurium, and polonium. And at the bottom there would be livermorium. And again, brand new, newly discovered element, and as far as I know, scientists aren't sure if it shares properties. So, the chalcogens have electron configurations that end with a p4, and so when they form ions, they're going to tend to gain 2 extra electrons. And so gaining 2 extra electrons, the ions that they form will end up with a -2 charge. Alright, finally, in column 15, just to the left of your chalcogens, you find the Nictogens. Nictogens, funny word, starts with a P. Right? Nictogens are also often called the nitrogen group because people don't remember the word Nictogen and nitrogen is at the top of the group, right? The group consists of nitrogen, phosphorus, astatine, antimony, and bismuth. And these elements tend to have an electron configuration that ends with a p3. And because it's a p3, these elements will tend to gain 3 extra electrons when they form ions, forming ions with a -3 charge. And again, the one at the bottom of the column, the Moscovium, brand new, recently discovered, and as far as I know, scientists aren't sure if it shares properties with the other one. Alright, so there was a little bit about some of the families of elements. We talked about hydrogen, we talked about the alkaline metals, the alkaline earth metals, and on the other side of the periodic table, we talked about the noble gases, the halogens, the chalcogens, and the Nictogens. So hopefully that helps us to be able to describe the organization of the periodic table. Until next time, take it easy.